Welcome to the Mistequa Wastewater Treatment Facility Expansion Project, conducted by Natural Infiltration Initiative, a team made up of 6 environmental engineering students, each with a diverse range of experience and expertise in a variety of fields, including hydrology, hydraulics, water treatment, and more. The wastewater treatment facility is located just south of Chuela, Washington, and is owned and operated by the Spokane Tribe of Indians. Built in 1999, the facility currently consists of a 115,000-gallon treatment lagoon, a 1 million gallon storage lagoon, and 2.5 acres of constructed wetlands. Currently, flows of around 17,500 gallons per day in the summer and 12,500 gallons per day in the winter flow directly to the treatment lagoon and then to the storage lagoon, where it is held until it is dosed into a series of constructed wetlands. Treatment of the wastewater begins in the treatment lagoon, which serves to reduce the biological oxygen demand of the incoming waste through a process which uses sunlight, algae, and anaerobic bacteria to reduce BOD below the acceptable threshold. After moving from the treatment lagoon, treatment processes continue in the constructed wetlands, which are a cost effective and relatively low maintenance treatment system that uses natural processes involving wetland vegetation and soils to improve water quality. All of the influent entering the wetlands must be handled through a combination of infiltration through the wetland soils and evapotranspiration using the planted vegetation, with no allowable discharge out of the system. Presently, the system is equipped to handle influent from the Mistequa Casino and its surrounding buildings, but due to the construction of a hotel in the area, flows are expected to increase to 25,600 gallons per day, which necessitates an evaluation of the current system to determine the potential expansion needed to accommodate the proposed flow increase. To do this, 3 primary alternatives were evaluated. These include an expansion of the existing facility through increasing wetland area, increasing storage lagoon volume, or a combined approach in which both are expanded. In order to determine which of these options is most effective in addressing the increased demand, a comprehensive mass balance was developed, in this case referring to inflows and outflows from the lagoons and constructed wetland. 4 main components contribute to this balance, including precipitation, evapotranspiration, infiltration, and inflow, each of which vary depending on the month of the year. Values in every month for each of these components were assigned based on geotechnical testing data, local precip and ET data, and the projected flow increases. By looking at the relationship between each of these variables, the current and future performance of the system can be evaluated. The model demonstrates that while the current system functions as expected, if the capacity of the facility is not expanded, system failure in the form of overflows and discharge will occur. By modifying values in the model to reflect each of the 3 expansion propositions, it was first determined that the alternative of a pure storage expansion would not be sufficient to accommodate the future demand, due to the infiltrative capacity of the wetlands being overwhelmed. The alternative of a combined approach demonstrated that a wetland expansion factor of 1.6 and a storage expansion factor of 2 would be sufficient, as would the alternative of a pure wetland expansion factor of 1.87. To select which of these alternatives to pursue for the final design, a multi-criteria decision analysis, or MCDA, was implemented, where the alternatives were weighed against each other using parameters of cost, ease of maintenance, and treatment efficiency. For all parameters, each criteria received a ranking from 1 to 9 when compared to the other options. Overall, the MCDA indicated a preference for alternative A, followed by alternative C, and then alternative B, with scores of 0.67, 0.24, and zero point zero 0.09 respectively. Therefore, alternative A, the 1.87 times wetland expansion, was selected. In determining the exact location this expansion would occupy, proximity to existing infrastructure, property lines, and waterways were considered. With these criteria, it was determined that a location just south of the current plan would be optimal. The total expansion area was then divided into 4 cells within the selected zone, which roughly equaled the area of each current cell. Requirements for distance between dosing ports, pipe connections, berm heights, and associated dimensions were all modeled within Civil 3D. Detailed specifications, such as elevations, areas, and component locations and labels, are all also included in the final CAD model. This system faces 2 additional issues that need to be addressed. The first of these is that the current influent screening unit is not operational, which allows for excess solids to enter the facility, reducing its overall efficiency. The second is that due to increased flows, the detention time in the treatment lagoon will be reduced such that the allowable BOD concentration of 100 milligrams per liter is no longer met. To address the dysfunctional influence screen, 3 main options were reviewed. 1. Replacing the existing bar rack system with a finer bar screen to allow fewer solids through, as well as installing bristle cleaners and a collection bin to prevent buildup and streamline maintenance. 2. Installing a parabolic bar screen which has no moving parts and also requires very little maintenance, though has a higher upfront cost. And 3. Installing a drum screen, which has several advantages, including additional BOD removal, but requires electricity to run and a high initial expense. Due to the upfront cost and resource requirements of alternate systems, replacing and upgrading the current bar rack system was chosen. As for the issue of meeting the allowable BOD requirement, a variety of systems that introduce atmospheric oxygen into the lagoon in the form of aeration were examined. These included an anti fouling aspirator aerator, tornado surface aspirating aerator, and a floating brush aerator. Each of these options require comparable maintenance and are capable of reducing BOD concentrations back under the acceptable limit. So the primary deciding factor was the cost to performance ratio of each system, in which case the anti fouling aspirator aerator won out. If this combination of facility expansion, influent screening replacement, and aeration solution is implemented, Natural Infiltration Initiative is confident that the Mistequa wastewater treatment facility will be prepared to handle the projected demand increase by a comfortable margin, and is pleased to have been given the opportunity to provide our services. Thank you to Tanner Germanson at JUB Engineering for providing resources and support throughout this project, and thank you for watching.